Okay, so again, tell me whenever you see my screen.
I can see it.
Okay. Okay, so again, hello guys, because we just started recording. Let's, without further ado, let's start group theory. So today we're going to continue with group theory, and we want to think about some questions about groups. So first question, let's start. So the first question, we are thinking about the group G, which simply is the set of 2 by 2 matrices, A, B, C, D, where these numbers are real numbers, A, B, and C, D are in R, and the determinant of this matrix is non-zero. Okay, so we have a set of matrices with non-zero determinant. We want to show G is a group. And the point is that I want you to fully prove it. I want you to prove everything you claim. Okay, so it's not very hard, but it's not very trivial. So think about that for a few seconds. I want to show this is a group. What is the first step to show that this thing is a group?
Needs an identity.
No, something even before proving it.
Closure.
Yes, we should show G is closed. G is closed. So let's try it. So let's say A is an element in G, B is another element in G. And we want to show A, B is an element in G. A times B is an element in G. But what is the requirement for A, B to be an element in G? Well, multiplication of two by 2 matrices, 2 by 2 real matrices, is another 2 by 2 real matrix. So that's kind of trivial. The only thing which remains to be checked is the fact that the determinant also should be non-zero. So I need to show determinant of AB is not 0. But we already assumed A and B are in G, which means determinant of A is not 0, and determinant of B is not 0. So that's the assumption. The assumption is that determinant of A and B, those determinants are non-zero, and I want to show determinant of AB is non-zero. How can I do that? So show determinant of AB is not 0. Okay, what is determinant of AB? Does anyone know what is it equal to? There's an easy formula for determinant of A times B.
Well, the determinant of any 2 by 2 matrix is AD minus BC.
That is correct. That's definitely correct, and I'm going to use that. But before that, what is determinant of multiplication of matrices? How is it related to determinant of A and determinant of B?
Is that equal to the determinant of A times the determinant of B?
Yes, that's correct. So determinant of AB is determinant of A times determinant of B. And because A is in G, this is non-zero. And because B is in G, this is non-zero. And of course, multiplication of 2 non-zero numbers is another non-zero number. But the only problem here is that in exam, well, it depends. Here, I want you to prove everything, including this formula, which you mentioned and is correct. So I want to prove that determinant of AB is equal to determinant of A, determinant of B. Has anyone seen the proof? Does anyone know how we can prove this thing? Okay, so if not, in general, this is correct in general. So this is correct for, A and B being any n by n matrices. And the proof in general is a little bit hard. It's not very hard, but it's not very trivial. One way to prove it is with using induction. But we don't need to prove it in general case. Remember here, we are only working with 2 by 2 matrices. So we only need to prove it for the case where n is 2. We only want to prove it for 2 by 2 matrices. And as you mentioned, for 2 by 2 matrices, there is a simple formula for determinant. So if A is, say, A, B, C, D, and B is E, F, G, H, we want to show determinant of AB is equal to determinant of A, determinant of B. So AB is equal to AE plus BG, AF plus BH, CE plus DG, and CF plus DH. That's AB. Now, we have determinant of AB. Well, as you know, determinant of a 2 by 2 matrix is multiplication of these two elements minus the multiplication of these two elements. So this determinant is equal to AE plus BG times CF plus DH minus AE plus BG, minus did I miss something there? There was C here. CE plus DG times AF plus BH. Okay, is that clear? That's just AB and that's just its determinant. Now, determinant of A is equal to AD minus BC. Determinant of B is EH minus FG. And determinant of A times determinant of B is just the multiplication of these two, which is AD minus BC times EH minus FG. So we should just check that this thing circled by red line is equal to this thing circled by blue line. And it's not very hard. We can just do the multiplication here and really see these two things are equal. I'm not going to do that, but it's not hard to do. But the reason I am mentioning that is that it's not, for you to see this is not easy if n is something but 2. So if n is equal to 2, these computations are not very hard. But if n is 3 or for any other n, these computations, they are non-trivial. So these computations, they become a little bit harder. So we really need a technique to do that. And the technique is induction. Anyway, but in this case, we don't really need that. So remember, this might look trivial, but you should always check the closure first. And in some cases, proving the closure is not very simple. Okay, as you mentioned, the second case is identity. Of course, there is identity element, and then the last one. Well, also we know multiplication of groups is commutative and associative, and we should check if we have a 2 by 2 matrix, its inverse is also a 2 by 2 matrix, which its determinant is non-zero, and that's the case here because if determinant of A is non-zero, determinant of A inverse is also non-zero. That's because A times A inverse, by definition, is the identity element, which here is the identity matrix. So determinant of A inverse is equal to determinant of I. But as we saw earlier, determinant of A inverse is determinant of A times determinant of A inverse. And determinant of the identity matrix is just 1. So determinant of A inverse is 1 over determinant of A. And if determinant of A is non-zero, 1 over that is still non-zero. So if A is in G, A inverse is also in G. Therefore, it's a group. Okay, is everything good? Do you still see the screen and have my voice?
Yep.
Okay, very good. Okay, so you can try the same thing as an exercise. I just here did it for n equals to 2. You can try it for n equals to 3, and you would see it becomes really harder to prove determinant of AB is equal to determinant of A times determinant of B if you want to do it kind of like brute force, because it's hard to compute really determinant of a 3 by 3 matrix. Okay, anyway. So now, for any group, we have a subgroup of that group called the center of a group. Center of a group. Does anyone know what is center of a group? Okay, center of a group G is the set of elements in G, where these elements, they commute with everything. Gx equals xg for any x in G. So, you know, in general, when we have a group G, in general, it's not abelian. Suppose it's not commutative, There are still elements in G which we show them with Z of G, center of G. There are elements in G which they still commute with every other element. Okay, so for example, we know 2 matrices don't commute in general. So A and B is not necessarily equal to BA. But if we take A to be the identity matrix times any matrix is equal to that matrix times identity matrix, because both of them are simply B. Okay, do you have any other example but the one I mentioned? Any other example about identity which commutes with any other matrix? Any 2 by 2 matrix which commutes with every matrix B? Okay, what about this one? 2, 0, 0, 2. Does this one commute with any matrix B or not? Is it correct statement or it's not correct? Okay, you can just unmute yourself and tell me, because I think you know the answer. It's not very hard.
I'm gonna go with yes.
Yeah, that is correct. That's the answer is yes. Good. So the reason is that A is, well, it's 2002. I can write it as 2 times 1001. If I multiply every entry in this matrix by 2, I would get this one, right? So it's just 2 times this matrix. But this matrix is the identity matrix, 2 times AI. So AB is 2 times I times B, which is 2 times IB. But because I is the identity matrix, IB is equal to B, so it's just 2B. What about the other one, BA? BA is B times 2I. The point is that when we have a number, real number, and a matrix, they do commute. So B times 2 is the same as 2 times B. And then there is this matrix I. So the numbers, they commute with matrices. So 2 comes here, and BI, because I is identity, is just B. So we get 2B again. So as you can see, both of them are equal to 2B. So they are equal to each other. So up to this point, we have shown that, so we just showed this matrix commutes with everything. This matrix also commutes with everything. So of course, for example, 3003 is similar. As you can guess, any number A, non-zero number A, 00A commutes with everything. So these are so-called in the center. We call them, well, the set containing all these things is called the center of, it's called the center of group. So these are in the center of the group. Do you know any other example but these matrices I mentioned? Do you think, is there anything else in the center? Is there any other matrix which commutes with every matrix? Or do you think it's all? You think there is no other example? Do you have any guess? You can just guess. Even guessing sometimes is not very bad. You should guess and then try to prove or disprove your guess, your conjecture. What do you think? Do you think, is there any other element with this property?
This might be like a dumb example, but what about like the zero matrix? Like all entries are 0.
You are definitely right, but the point is that zero matrix is not in the group we are studying. Zero matrix really commutes with everything, because zero matrix times anything equals that times 0, because both, well, you know, 0 times anything is 0. And so it is correct. 0 commutes with everything. But at this point, we don't say 0 is in the center of G, because center of G, we define it as the elements in G, in our group, which they commute with everything else in G. And the definition of G was the matrices which their determinant is non-zero. But determinant of this matrix, 0, 0, 0, 0, its determinant is 0. That's why. But you are right. This matrix commutes with other matrices.
Gotcha.
Okay. What about this one? 1, 0, 0, 2. Does this one commute with other matrices, other invertible matrices? Let's try. Let's try to see if it really works or not. We want to see if this thing is equal to b times 1, 0, 0, 2, right? So the way to solve these things is to really write something for B. So B is just a generic matrix, and any generic 2 by 2 matrix can be presented with something like that, a table of 4 numbers, A, B, C, D. We want to see, so we don't know, we want to see if A, B, C, D times 1, 0, 0, 2 is equal to 1, 0, 0, 2 times A, B, C, D, right? This is what we need to check. Okay, let's compute the left-hand side. This multiplication is going to be equal to 1 times A plus 0 times C, 1 times B plus 0 times D, 0 times A plus 2 times C, and 0 times B plus 2 times D. What about the right-hand side? The right-hand side is equal to A times 1 plus B times 0. A times 0 plus B times 2, which is 2B. C times 1 plus D times 0, which is C. And C times 0 plus D times 2, which is 2D. And as you can see, these two matrices are not equal. They are not equal. Therefore, these are not equal. Therefore, these are not equal. So this new matrix, 1, 0, 0, 2, for example, this one is not in the center of the group. So it makes sense to guess that the center of the group contains only the elements which I mentioned, A, 0, 0, A. And because we want the determinant to be non-zero, we should assume A is not 0 itself. Okay, now we should prove that. How can we prove this thing? How can I prove such a thing? So the way to prove it is by kind of, well, let's write down the definition. So suppose A is an element in the center. And what I want to prove is that I want to show A is equal to A, 0, 0, A for some A for some A non-zero, right? That's what I want to prove. Okay, this is 0. Okay, so it means AB should be equal to BA for every B in our group, right? Again, any 2 by 2 matrices, in this case A, has a generic form. It's like A, B, C, D, right? So in other words, AB equals BA, in other words, would be A, B, C, D times the matrix B should be B times A, B, C, D for every B. Now, we should take advantage of this fact that we can have any B we want, as long as this map B is invertible. So I can choose some specific B and it should be still correct. So if if we choose B to be this matrix, for example, say 2, 0, 0, 1. It's very explicit example, right? This matrix is in G because it's the determinant here, the determinant is equal to 2, which is non-zero. So the matrix A should commute with this matrix. So we should have A, B, C, D times 2, 0, 0, 1. It should be equal to 2, 0, 0, 1 times A, B, C, D. Right? We should have this equality. Because we should have this equality for any B, therefore, this is a very explicit B. It should be correct for this explicit B too. Is it clear what I'm doing? Is there any question? Okay, I take it as no. So let's see. This multiplication would be 2A plus 0, B, 2C, and D. And this multiplication would be 2A, 2B, C, and D. And we want these two to be equal. What does it mean? It means they should be, each entry here should be equal to the corresponding entry here. So 2A should be equal to 2A, that is trivial. B should be equal to 2B. What does it mean about B? If B is equal to 2B, what does it mean? What can we say about B? It means 2B minus B should be 0, therefore B should be 0. Right? Now 2C, oh, sorry. 2C should be equal to C. Similarly, that means C should be 0. And then finally, it means D should be equal to D, which doesn't really matter. So this matrix A, it has A, B, B should be 0, C, C should be 0, and then D. Okay, so the matrix A should be of this form. Necessarily, it should be A, 0, 0, D. But still, we are not finished. It doesn't mean anything of this form is in the center. I chose one explicit map D. Okay, let me continue somewhere else. Now I can choose I chose explicit matrix B. I can choose another matrix B. So right now I know if A is in the center, A is of the form A, 0, 0, D. Now I know AB should be equal to BA for any B in G, for all B in the group G. Now I can take another matrix B. Let's take B to be, well, let's take it to be 1, 1, 0, 1. Determinant of this matrix is 1. 1 times 1 minus 1 times 0. And this is non-zero. Therefore, B is in the group G. So we should have this equality AB equals BA for this specific matrix too. A is equal to A0, 0, D. Therefore, A0, 0, D times 1, 1, 0, 1 should be equal to 1, 1, 0, 1 times A0, 0, D. Let's do this computation.
I just have a question. How are you getting the 1, 1, 0, 1?
I kind of randomly chose that matrix. The only thing I had in my mind was that I want the determinant of this matrix to be non-zero. And I'm quite sure if you just choose another matrix, like some other thing, it would work perfectly fine. I'm just choosing a few different matrices. You know, it's just like testing. So it's not really something like there's no really idea behind this. I'm just choosing a matrix which its determinant is non-zero. And I hope it would work. If it doesn't work, I would try with something else. So this multiplication would be A, 0, D. What about this multiplication? It would be A, D, 0, D. These two have to be equal. What does it mean? A should be equal to A should be equal to D. And the last one says D should be equal to D. So up to this point, we knew the matrix A is A, 0, 0, D. But here we just learned that A is equal to D. So A, 0, 0, instead of D, I can write A. And that's it. That's exactly what we guessed. So the center of this group consists only of these matrices, which I can write it as A times 1, 0, 0, 1, which is A times identity matrix. And that's it. That's the center of a group. Now, if you're not really familiar with this concept, it's a good it's something interesting to practice. You can go back and look at the examples of the groups you know, and you can compute the center of these groups, the elements in these groups, which they commute with everything. Okay, so for example, if the group G is abelian.
Can you just scroll up a little bit? I just didn't get the last part.
Here.
Yeah, that's good right there.
Yeah. So yeah, so here yeah, so here I just took the matrix B to be 1, 1, 0, 1, and then I wrote down the equation AB equals BA. I computed AB, I computed BA. I want them to be equal, so A has to be equal to D. So A is equal to A, 0, 0, D, but if D is equal to A, I'm gonna get A, 0, 0, A, which just means A times the matrix 1, 0, 0, 1, which is the identity. Okay, now if the group G is abelian, what is the center of the group? If we know G is abelian, what is its center? What does it mean for G to be abelian? It means all the elements in G, they commute with each other, right? Now, center is the elements of G which they commute to with other elements of G. Now, can you guess what is the center of the group if the group is abelian? For example, let's look at an example. Let's look at a commutative group. For example, we can G to be the set of integers with addition. What is the center of this group? It's everything, right? Because everything commutes with everything else. For any two numbers A and B, they commute with each other.
I have a question.
Yes.
Maybe not like a question, but like that's what I was thinking. So like if G is is an abelian group, then the center of the group could be like anything in G, right?
Yes, that is true. That's indeed true. So center of G is all of the G. Yeah, that's correct. Now, what about the other direction? If we know the center of G equals G, what can we say about this group if its center is equal to everything?
Then the group is abelian.
Exactly, because if the center is everything, it means everything is in the center, which means everything commutes with everything else. And that simply means the group is commutative. So a group is abelian if and only if its center is equal to itself. That is correct. Okay, so that's the second part of this, our question. Okay, is there any question here? Okay, now let's take, say, O to be elements in G, matrix 2 by 2 matrices in G with the non-zero determinant such that A times A transpose equals identity. We want to show this thing is a subgroup of G. Remember that if A is a matrix A, B, C, D, A transpose is AB, CD, is AC, BD. So the first row becomes the first column, and the second row becomes the second column. We want to show this set is a subgroup. Okay, we can think about that for a few seconds. Okay, how should we prove something is subgroup of something else? In general. So in general, what is the method of proving O is subgroup of G? Is it the notation you use for subgroup? Okay, so O is a subgroup of G whenever for any two elements A and B in O, for any two elements A, B in O, A times B inverse is also in O. Are you familiar with this lemma? So A is a subgroup of G if and only if for any two elements A and B in O, A, B inverse is also an element in O. So here, I'm assuming A and B are in O, which means A transpose equals identity. B is in O, which means B transpose is equal to identity. This is what I know. What I want to prove is that AB inverse is in O, which means AB inverse times AB inverse transpose equals identity. So because I want to show this matrix is in O, I should show this matrix times its transpose equals identity. That's what I need to put. Okay. So I have AB inverse transpose. What is AB inverse transpose? What does it equal to? Does it equal to A transpose B inverse transpose? Is this equality correct? Do you have my voice? Okay, so this is not correct. AB inverse transpose actually is equal to B inverse transpose A transpose, which is equal to B transpose inverse A transpose. So if we go back and look at what we have above, we have AB inverse, B inverse transpose, A transpose. Okay, what can I do with this one? What can I say about that? So the point is that if you look at this part, I have B inverse times B inverse transpose. This thing is equal to B transpose B, everything inverse. I can bring out this inverse in transpose. And because B is in O, B transpose B is equal to identity. So I have A identity inverse, A transpose. So it's just A transpose, which is A transpose, which is equal to identity. And that's what we wanted. So this shows O is indeed a subgroup of G, which is what we wanted. Okay. Okay, so let's go back. Okay, sorry for the kind of delay we had and a little bit difficulty. I'm not still 100% sure why we had this problem. So if there is no question, you can ask any questions you have today or tomorrow about your homework, and we can discuss them through Zoom. And next week we would start with polynomials, and they are really interesting. That's a really interesting subject too. So until then, if there is no question, stay safe. Goodbye, guys.